Class, welcome back to the session of the Bode plots, class number 2. Yes, very good afternoon, everyone. I hope you had your lunch properly. This is the continuation of the first class. Now, we were talking about the problem. We shall continue straight away from that problem. Yes, very good afternoon, everyone. With a good enthusiasm, let us begin with our Bode plots, class number 2. Okay, continuing with the same question. Right? So come on quickly, let's let everyone join the session quickly fast. It's 2 p.m. Second class today is all complete day dedicated towards Bode plots. All three classes of Bode plots. Yes. So this is the question that we were going through. And we had completed the steps. Only thing is I told we'll be starting the sketches of this. Okay. Yeah, good afternoon once again, everyone. So we'll directly start with the sketches of this. Yes. So first of all, we converted the transfer function into standard form. These were the results. Then we determined the corner frequency. This is just reviewing quickly. There is no corner frequency due to the zeros, and there are two corner frequency due to the pole, that is 2 and 12.5. Then we decided the starting frequency as 1. The rule was 10 raised to the power m less than all the corner frequency. Then we talked about the initial part of the Bode plot. Initial part from the starting frequency up to the first corner frequency. Starting frequency up to the first corner frequency is the initial part. So we talked about the initial part. Alright. And using the formula, this is the important formula for initial part, minus 20 and log omega plus 20 log k. N equal to 1, k equal to 4 substitute kiya. N equal to 1 and k equal to 4 substituted. And we got this as the magnitude function, minus 20 log omega plus 12. We calculated the magnitude at both the ends of the initial part, omega equal to 1 and omega equal to 12. The results are obtained in front of you, 12 dB and 6 dB. Then we went on for some phase calculation. Guys, if it is buffering for you, please refresh it once. I'll just suggest you to refresh it once. These are the phase calculations, minus 90 minus tan inverse omega by 2 minus tan inverse 2 omega by 25. And as I told, we will be now taking the actual phase calculations. And these are the phase values for different omegas. I took omega equal to 1, starting frequency, first corner frequency, second corner frequency. Then randomly I took a value 20, and then moving towards infinity, we observed that the phase is moving towards minus 270 degree. Okay, in between 2 and 12.5. There is a point where the phase in between has crossed away minus 180 degree, and that is known as the phase crossover frequency. Okay, and only thing I asked you to complete was to calculate the phase crossover frequency. So let us continue now. Yes, Shubham, correct answer. Almost many of you given the correct answer there in the first session only. Omega p, I told you, just take 2 minutes, you can solve it. Yes. Omega p, if you are able to see that, the GSHS is of the form k by s, 1 plus st1, 1 plus st2. It is of that form only. Now look at this, k by s, 1 plus st1, 1 plus st2 is the GSHS given. So what is the omega p for this? The omega p is given by 1 upon under root t1 t2. Otherwise there is the general method. Only for this function I've told you to remember. Only for this function. Otherwise we can calculate generally. And this is 1 upon root t1 t2. The 1 upon root t1 is half. T2 is 2 by 25. 2 and 25 cancel, 2 and 2 cancel, 25 upar jayega, under root of 25 is 5. Okay. Okay, so from here actually we are starting our class number 2. Class number 2, that is omega p. Omega p is 5. I asked you to calculate this. Yeah, other way, Shivans, the same yesterday class. हम क्या कर रहे थे? Equate the phase to minus 180 degree. Equate the phase to minus 180 degree, simplify in terms of tan inverse and get the phase crossover frequency. Yes, like yesterday's class, we had solved so many questions yesterday regarding the omega p, omega g, gain margin and phase margin. Now guys, time to come for the plots. I'll put it as step by step. put it as step-by-step sketching of this one. Start from here. Alright, so just keep on focusing with me. Let us do it step by step. It's a simple calculation. Now we all know what is this scale is the log omega scale, and this is my magnitude scale in decibel. This is my magnitude scale in decibel. What are the important frequencies? Let us write down those important frequencies. Starting frequency क्या है मेरा? Now refer to the step. Starting frequency is 1. So here I will be putting down omega equal to 1. Okay. Then we have the first important frequency, that is the corner frequency. Okay, omega equal to 1 pe what is the magnitude is 12 dB. Omega equal to 1 pe the magnitude is the 12 dB. I am taking divisions of 5 each, and here it is my first magnitude. I can put it here. Say this is 12 dB. Okay, I'll hide my view after some time. Let us just understand first. So this is 12 dB. Okay, and omega equal to 2. Okay, the frequency, the magnitude is 6 dB. At frequency equal to 2, the magnitude is 6 dB, so approximately here. So guys, sketching my initial part. I'm just sketching my initial part. Just focus with me. This is my initial part. I will highlight this frequency as my first corner frequency, that is equal to 2. I will stop. See, what is the initial part from omega equal to 1 up to omega equal to 2. Up to the first corner frequency is the initial part. Initial part, as I've explained in the last class, is also a straight line having a slope of. Initial part is a straight line having a slope of minus 20 decibel per decade. Minus 20 decibel per decade, right? The slope line, initial part having a slope of minus 20 decibel per decade. Okay. So this line has a slope of minus 20 decibel per decade. Now I stop at the corner frequency. Why do I stop at the corner frequency? Because at every corner frequency, what occurs is a slope change. What occurs is a slope change. Now this is the corner frequency due to what? This is the corner frequency due to pole. All the corner frequency are due to the pole. There is no zero here. So what will you do for the corner frequency which is due to the pole? You will change the slope by, minus 20. So already the current slope is minus 20. Decrease the slope by minus 20. You get minus 40. Minus. So whenever slope is changing minus, bend the line downwards. And whenever the slope is changing upward, positive, so bend the line upwards. Bend the line upwards. Take it like that. So suppose if there was no corner frequency, then this line would have extended with the same angle, same slope. But because there is a corner frequency, the slope will change, bendwards, it bend downwards, and here I am going to change the slope. Just bend it little bit downwards. Just slightly bend it little bit downwards. Now, till where? Where will you take this line up to? Take this line up to the next slope change point. Next slope change point is the next corner frequency in sequence, and that is equal to 12.5 now. The next corner frequency 12.5. So take this line up to the 12.5, but at the 12.5, okay, what is the magnitude? What is the magnitude at 12.5? Can we calculate that? I will again sketch it fairly. I'm just doing the rough calculation. Now this line has a slope of minus 40. This line has a slope of minus 40. So it goes on up to the next corner frequency. Next corner frequency 12.5. What is the magnitude at 12.5? First, let us calculate that. I am giving you the graph with all details available. Okay, then we will see the quiz sketching. MCQ question from Bode are very simple, but pehle concept should be clear for everyone. So what is the magnitude at 12.5? I am now trying to find, guys, what is the magnitude at omega equal to 12.5. For that, I will again use the slope formula. What is the slope formula we have discussed in the last class? It is actually y2 minus y1 by x2 minus x1, but you will use m2 minus m1 divided by log omega 2 minus log omega 1. Okay. All right. So use this formula. Use this formula. The slope of the line that you are discussing right now, the new line is minus 40, is equal to m2, the new magnitude, minus what is the magnitude that this line is starting with? It is starting with 6. This is what I have highlighted here, 6. So m2 minus 6 divided by log of omega 2. It is going till omega 2 matlab 12.5. And what is the frequency? It has started with the corner frequency 2. It has started with this frequency equal to 2. So log of omega 2 minus log of omega 1 I have written here. Solving this, what is the value of m2 that you should get? M2 is equal to minus 40 log of a minus log of b, divide kar dete hain, so it becomes 12.5 by 2 plus 6 on the other side. Let us calculate this. Okay, let us calculate this. You can use your calculators. Remember, base 10 hai. So this is coming up as minus 25.8 decibel approximately. Minus 25.8 decibel approximately. All right, minus 25.8 decibel approximately. So I will just highlight this. This is a, if I again take the same divisions of 5, yeah, approximately let's take minus 25. थोड़ा सा मैंने इसको चेंज करता हूँ. Now that's the biggest problem. There is no undo option with this eraser mode. Yes. Let's take it approximately as minus 25 only. Okay. So now that means, now I will erase these rough sections. These were all rough things that I was showing you. I'll sketch it now. These were the rough things, how the line will start. Okay. So now I will continue this line, and this line will touch minus 25. This line will cut minus 25. I'll hide my view. Just wait for that. Don't worry. This is what I'm taking a line from minus 25. The magnitude should become minus 25 at the next corner frequency. At the next corner frequency, the magnitude should become minus 25. Okay. So let me continue this line now, and we will extend it to meet this line, and the frequency here should be 12.5. Let us write down that frequency also. Frequency here, this frequency here is 12.5. Now guys, once again listen with me. If this was not a corner frequency, suppose if this was not a corner frequency, line will extend with the same direction, with the same slope, but this is a corner frequency, and corner frequency due to pole. Okay, the slope of this line is minus 40 decibel per decade. Let us also write that, minus 40 decibel per decade. And now again a pole, and what is the slope change due to pole? Further minus 20. So minus 40 minus 20, the line slope will now be minus 60. Matlab again bending downwards. So again it should be bending downwards. It's not following this direction. It is going to bend downwards once again. So just bend it downwards, approximately freehand sketching. Just bend it downwards. Okay, and the slope of this line will be minus 60 decibel per decade. The new line will have the slope of minus 60 decibel per decade. Okay. This is my magnitude plot completed. This is my magnitude plot completed here, right? This is the magnitude plot. Okay, guys. Now, starting with the phase plot also. So just follow for the phase plot with me. Let us go for the phase plot. Phase in degrees, magnitude in decibel. We all know the basic units, magnitude in decibel. Now, listen to an important point and I will explain about that also. But just first listen with me. As I told in the beginning, okay, 2 dB means magnitude is 2 dB only. You are telling the magnitude 2 dB, so it is 2 dB only. Yeah, Anjana, the pole at origin is represented here in the initial part. I told her what is the slope of the initial part. There was a formula of initial slope that we discussed, and that was equal to minus 20n, where n is the number of poles at origin. So that is why the initial slope is minus 20, because n is equal to 1. So that is how the slope pole at origin. The pole at origin will be affecting the initial part. Okay. Other poles will be affecting at the other parts, the corner frequency. Guys, listen with me now. As I told in the Bode plot, we will be superimposing the magnitudes, and the phase plot all together. Manan, keep concentration in the class. Omega equal to 2 pi magnitude 6. I already calculated. Okay, so keep on following. Do not miss any calculation. Whatever is done is 6 dB. It is written there. We calculated in the last class only. Okay, so magnitude and phase plot, it is overlapped on the same thing. So that is why I am doing the calculations in the plotting the phase plot here also. Guys, now because it is the same plot, how do you sketch any plot? Listen now, important concept ki baat kar rahe hain hum. Now, how do you plot anything? This is the x-axis and this is the y-axis. So where I should actually do the phase calculation, I should plot the phase here only. This is my y-axis. Here only I will plot the phase. Okay, so my phase plot will start from this y-axis only. But if I show the value of phase here, what is the phase? Suppose it is minus 120, minus 150. So if I write down the value of phase here only, so these values and the phase value will be a little haphazard, hosh-posh ho jayega, and you will not be able to understand the graph. Isliye what is done? An alternate y-axis, as you are able to see, I have created a vertical axis again. That is known as alternate y-axis only for reading. Only for putting down the reading. But actual y-axis will remain as the same. This is the y-axis. But to write down the values of phase, I am using this value to represent the value of phase. This one. Okay. And whenever you do a y versus x graph, on the x-axis, what is the value of y? It is taken as 0. On the x-axis, the value of y is taken to be 0. So what is phase? Here I should take it as 0. But it is not actually taken as 0. The phase on the x-axis here is taken as minus 180 degrees. Why so? I will explain it shortly. So always on the x-axis, phase will not be taken as 0. It will be taken as reference value of minus 180, and why so we will understand that. So my fast calculations that we have done in the last class, it is there in front of me. I need to plot these values of phase. And looking into this, I am able to read. Let me take a subdivisions of, just a second, this is 1, this is 2, let's take this is 3, and here also I'll take subdivisions of, I'm taking subdivisions of 30, guys. Okay, so 30 means this is upar jayenge to minus 150, this is minus 120, below minus 210, minus 240, and finally this will be minus 270 degree. Okay, just randomly taking subdivisions of 30. Looking into the phase value, my first phase value is minus 121. Now listen, I'm starting the phase plot now. Guys, listen very carefully. My first phase is minus 121, that is here. Okay. But as I told, this is not the y-axis. Y-axis is the same. One graph, One graph will have only one y-axis. So phase यहीं से start करोगे. Only thing is to write down the value of the phase. I have created a parallel y-axis. So 120, 120, 121. Approximately it is coming here. Okay. Just take 121. It is approximately coming here. My next phase value 144 at omega equal to 144. So 144 matlab just above 150 somewhere here. Okay, just somewhere here. My next phase value 216. 216 matlab below the x-axis it will go at omega equal to 12.5. Next corner frequency, this one, 216. Next is 232. 232. Finally going towards minus 270. Finally going towards minus 270. So what I will do, just have a free hand curve. Free hand curve joining these points. Okay. First 2 points. Now take it towards the next one and then finally take it towards minus 270. Just a freehand sketch is sufficient. Just a freehand sketch. Finally tending towards minus 270 degrees. Finally going towards minus 270 degrees. Correct? Minus 270 degree. Finally going towards this. This is minus 144. This face is minus 121. This is the only y-axis. I have started from y-axis and moving further. Okay. Now guys, tell me some important things. Tell me some important things. What is this and what is this frequency? What is this frequency? Now we will discuss more about this plot. What is this frequency, guys? What is this frequency? This is the frequency at which the phase is minus 180 degree. Okay, the phase is minus 180 degree and that is known as omega p, and that we have already calculated. My homework, that is 5. Okay. And what is this frequency? This one. What is this frequency? Can we say what is this? Just name this frequency. Just name this frequency. Yes, it is the gain crossover frequency. Now, I'll just put down the remarks. What we have learned yesterday, at omega equal to omega g, the magnitude is equal to 1. What was the gain crossover frequency? The frequency at which the Nyquist plot cuts the unit circle. Okay, magnitude equal to 1 in the form of decibel. In the form of decibel, magnitude is equal to 20 log 1 and log 1 is 0 dB. So whenever the magnitude is 0 dB in the form of decibel, that frequency is omega g. That frequency is omega g. So I will come and represent here. This frequency is omega g. Can we calculate by the Bode plot? Can we calculate by the Bode plot? Can we calculate this frequency by the Bode plot? Okay. So from calculating from the Bode plot, again by the formula, slope equal to m2 minus m1 divided by log omega 2 minus log omega 1, slope formula. What is the slope of this line? Okay, the slope of above line I have erased. I will write it first. The first slope was, this was minus 20 decibel per decade. Okay. The slope of this line is minus 40. So write down the slope of the line minus 40 is equal to, pick any 2 points. Suppose this is 1 point. Pick this point and pick this point. These 2 points I am highlighting right now. Then I will erase. So 0 minus, what is this magnitude? 6. Already we have calculated. 0 minus 6 divided by log of omega g minus, what is the frequency here, is 2. Minus log of 2. Okay, so calculating this, log of a minus log of b is log of a by b. Log of omega g divided by 2 is equal to minus 6 by minus 40. Okay, minus 6 by minus 40, that will come up as 0.5. So what is omega g divided by 2? To eliminate log, take 10 raised to the power 0.15, and finally solving omega g kitna ho jayega. So let us calculate that. I have 10 raised to the power 0.15, that is 1.41 into 2. The omega g is coming as 2.82. Omega g is basically coming up as 2.82. Okay, radian per second. Let us write down that value in the graph. Okay, so this is 2.82 radian per second. So this is omega g. Done. The omega g is done. Acha, we shall also go for gain margin and phase margin with this question. But guys, can you tell me for this question, looking into this much, whether the system is stable or unstable? Can you tell me stable or unstable? Can you comment on stability, whether it is stable or unstable? By the comparison of omega g, omega p, I told you one method yesterday, na? Omega g is less than omega p, meaning that the system is stable. Omega g less than omega p, the system is stable. Okay. Now this should also be clear by the gain margin and the phase margin. Okay. So now how to calculate the gain margin here from the Bode plot? Gain margin ke liye we need omega p, that is equal to 5. Omega p is known to us 5. Okay. Now come to the gain margin calculation. What is the gain margin formula, guys? The standard formula of gain margin 20 log. Now you should understand why we define the gain margin in decibel, so that it is consistent with the Bode plot also, because Bode plot is sketched in the log. So 20 log 1 upon mod gj omega hj omega p. 20 log 1 upon mod gj omega p hj omega p in the form of decibel. Okay. What is log 1 by x? Is minus log x. So what is the gain margin? Is minus 20 log mod of gj omega p hj omega p. Log 1 by x is minus log x, and that means this gain margin is equal to minus c minus what is 20 log mod gj omega hj omega is the magnitude in the Bode plot. When I say, या हम बार बार बात कर चुके हैं कि when I say magnitude in the Bode plot, it is 20 log mod gj omega hj omega, right? So 20 log mod gj omega hj omega matlab magnitude on the Bode plot. So this is equal to minus of the magnitude reading, okay, magnitude reading from Bode plot at omega equal to omega p. So how do you find the gain margin from the Bode plot? How do you find the gain margin from the Bode plot? It is the negative of the magnitude reading from the Bode plot at omega equal to omega p. Negative of the magnitude reading from the Bode plot at omega equal to omega p. Right? So let us come back to the graph and calculate this. Let us come back to the graph. Okay, what is my graph? Omega p is equal to 5. What is the magnitude at this point? I am interested in that magnitude. Okay, what is the magnitude at this point? Let me highlight this point. Okay, and the negative of this value will be equal to the gain margin. Okay, the negative of this value will be equal to the gain margin. I will write down everything on this graph. Gain margin is equal to minus of the answer that you are going to get here. Negative of this value. Okay, so let us calculate this value. Now this value lies on which line? It lies on the line which has a slope of minus 40. Which has the slope of minus 40. Okay, which has the slope of minus 40. So we can again calculate y2 minus y1 by x2 minus x1. Use these 2 points to calculate. Okay, use these 2 points to calculate. So I am starting the calculation now. Okay, slope is minus 40 equal to magnitude minus 0 divided by log 5 minus log 2.82. Okay, just solving this, you get the magnitude as equal to how much? Okay, let us just try this. I am getting the magnitude as minus of 9.94, yeah, 9.95. Okay, so what is my gain margin then? What is my gain margin? This is negative of the reading obtained from the Bode plot. That is minus 9.95. Negative of this gain margin is actually positive only because it is stable system. 9.95 plus 9.95. Okay, the gain margin is plus 9.95. Got it? Now this is the gain margin calculation. Next, let us go towards the phase margin calculation. For phase margin, we need omega g. Omega g is just now calculated from the Bode plot. Just we calculated 2.82. So what is the phase margin? Is given by the formula 180 degree plus angle gj omega g. Guys, remember the formula na yesterday's class? Angle gj omega g hj omega g. So that is equal to 180 degree plus what was the angle gj omega g hj omega g formula? Minus 90 minus tan inverse. I'm just writing this formula again, the phase calculation. Minus 90 tan inverse omega by 2, tan inverse 2 omega by 25. Tan inverse omega by 2, omega is 2.82 by 2 minus tan inverse 2 into 2.82 divided by 25. Okay, just evaluate this and get the answer. Just let us evaluate this and get the answer. The phase margin, guys, is coming up as somewhere approximately 22.6 degree. Okay. Yes, 22.6 degree. Correct. Tally bhi kar liya. 22.6 degree, which is also positive. Gain margin was 9.95 decibel. Phase margin is 22.6 degree. मैंने बोला ही है, I've given you confirmation, both are positive and always both will be of same sign. Both are positive, so the system is stable. System is stable. All right. This is about the gain phase margin. Okay. Yes, understood everyone? Yes, guys, understood everyone? Just waiting for your brief comments quickly. Yes. Chaliye. Now, one last thing with this Bode plot, and then we'll take the screenshots and go for the next one. Go for the next one. Look at this, guys. Now, one more consideration. Yeah, Mahesh, that I have told yesterday also. Yesterday in some questions, in MCQ question, remember, I was just matching the option on this criteria only. One is positive, other will be by default positive. They will be of the same sign. Okay. Okay. Now listen to this point now. See, what is the final slope of this Bode plot? Okay. After this, there is no more slope change because there is no more corner frequency. So what is the final slope of this Bode plot is minus 60. And now why the final slope is minus 60? Understand this. Okay. First, the initial slope was minus 20. Why the initial slope is minus 20? Actually, the initial slope formula is minus 20n. Minus 20n is the initial slope formula. N is the number of poles at origin. Okay. So जितने origin पे poles होंगे, that many times 20 will come as the initial slope. Okay. Then there comes another pole. There comes another pole, the slope changes by minus 20, it becomes minus 40. Another pole, so it changes the slope by again minus 20. The final slope becomes minus 60. Okay. Final slope becomes minus 60. So suppose you have p poles and z zeros. Okay, p poles and z zeros. So for every pole the slope is minus 20. So for p poles minus 20p. For every zero the slope will be added by plus 20. Next example I am taking with zeros only. Okay, there will be some zero also. So plus 20 into z. Plus 20 into z. The final slope formula should be actually minus 20p minus z. Minus 20p minus z. Just look at this, given the final answer. The final slope and the final phase formula. The final slope of a Bode magnitude plot. Okay, what is minimum and non-minimum phase? I told I will explain you somewhere within Bode only. This given by minus 20 into p minus z. Minus 20 into p minus z in the form of decibel per decade. Okay, in the form of decibel per decade. I'll just mention that. Okay. Minus 20 decibel per decade. Okay. No, Manan, from this you can't conclude three poles. You can conclude that. From this Bode plot you can conclude. Yes. Yes. The final phase of the Bode magnitude plot for minimum phase systems is minus 90 degree into p minus z. Minus 90 degree into p minus z. Okay. Yeah, Shubham, that's like the diving angle only. Minus 90 degree into p minus z. But the final phase for Bode magnitude plot is valid for minimum phase system. Now, what is a non-minimum phase system? Okay, I'll explain you that. Okay, so just note down this formula. The formulas are sufficient. The final slope and the final phase. Final slope and the final phase. That is why the final slope, the final phase you see here. What is the final phase that you have seen in the plot is minus 270. Okay, 3 minus 0. Okay. Okay. Guys, time to take the screenshot from the beginning of this question. No, Zishan, I have not mentioned any method for calculating PM from the plot because, okay, I'll highlight in the plot also. Next screenshot. Because actually for phase we have not done any approximation method till now. Phase means actual formula. So I calculated with the actual formula. Only thing is phase margin is calculated at omega g. Omega g was calculated from the plot. Omega g was calculated from the plot, Zishan. Okay. Phase margin I will highlight in the plot. Let me come to that slide once again. I will highlight the phase margin there. Keep on taking the screenshots as well. Next one. Next. Next. Yeah. Here, guys, first I will mention the phase margin here. Then you can take the screenshot. See, phase margin is calculated at omega g. Okay. And the phase margin is what? 180 degree plus angle gj omega g hj omega g. Okay. And this is usually plus angle gj omega g likha to jata hai, but this is actually negative because of the clockwise movement that I have explained yesterday. See, this is the negative phase. So actually, what is the phase at this and what is the difference of the phase with the 180 degree line? This difference here. I'll highlight with some dark color. Yeah. This difference of 180 degree and angle at omega g, this difference is basically the phase margin that I can highlight in the plot. And that was obtained to be how much? 22.6 degree. Okay, let me write down the gain margin also on the plot. Let us write down the reading on the plot. As I told, gain margin is the negative of the magnitude obtained at omega p. So from this I am writing what is the gain margin is minus of minus 9.95. This was obtained as minus 9.95. So the gain margin was plus 9.95 decibel. Okay. Now you can take the screenshot. This is the complete Bode plot with all the details of omega p, omega g, gain margin, phase margin. So guys, suppose if you are sketching on a proper log paper, on a proper graph paper, so what you have to do from the graph paper, you will see ki what is this phase. That reading will you will take from the graph. That reading you will take from the graph. What is the reading at this? Okay. And what is the difference between that reading and the 180? That is the phase margin reading from the Bode plot. That is the phase margin reading from the Bode plot. Okay. Next screenshot. Next one. Next screenshot. Next one. Next screenshot. Next one. Okay guys, now starting one more example. Let's do one more so that we'll understand again the clear picture. Let's understand one more example. Sketch the Bode plot for the system having the open loop transfer function to s plus 0.25 upon s square, s plus 1, s plus 0.5. Okay, let us start this one. Bode plot for system having this open loop transfer function. Once again, number one thing that you will do is to convert into the standard form. Okay, basic points, let's do it very quickly. So what is GSHS? Converting into the standard form, this will become 2. One standard form means 1 plus st. So I take 0.25 common. 1 plus s divided by 0.25 is whole divided by s square. There is also a 0 term now. Into s plus 1 is simply 1 plus s. No need to take any common. Into 0.5. 1 plus s divided by 0.5. Okay. So 0.5 and numerator 2 into 0.25. Constant is cancelled. So what is the GSHS final form? GSHS final standard form, and that is equal to just 1 plus s by 2.5. Matlab 1 plus 4s. 1 plus 4s divided by s square. 1 plus s. S square 1 plus s. 1 plus s by 0.5. 1 plus 2s. Okay. 1 plus 4s upon s square 1 plus s 1 plus 2s. Okay. This is the final standard form. That means what is the value of n here is 2 and what is the value of k here is 1. Okay. The k here is 1. Okay. Now, what are the corner frequencies? What are the corner frequencies? Now, what are the corner frequencies due to the zeros? Omega equal to 1 by t. ठीक है, 1/4, ठीक है, and corner frequency due to poles omega equal to 1/1. One of the t time constant is 1, the other one 1/2. Okay, so it is equal to 1 and 1/2. So corner frequency is 1 due to 0 and 2 are due to the poles. Okay, write them separately because slope change effect is different for both. Slope change effect is different for both. After writing the corner frequency, what will you do? You will write down the starting frequency of the plot. So next is starting frequency of the plot. Okay. Starting frequency of the plot. So what is the starting frequency? I've told you take omega equal to 10 raised to the power n less than all the corner frequencies. The corner frequencies are 1/4, 1/2 and 1. Okay, that is 0.25, 0.5 and 1. So what is omega? You can choose it at 10 raised to the power minus 1, that is 0.1, which is less than 0.25. So obviously less than 0.5 and 1. So 0.1. 0.1, correct? So starting frequency, yes, everyone now writing correct. 0.1 is the starting frequency. 10 power m के form में लेना है. What is the value of m? And that all depends on the question depends on the corner frequencies. Okay. After that, I write down the initial part calculation. Initial part matlab the part of the Bode plot from the starting frequency up to the first corner frequency. First corner frequency 0.25, starting frequency 0.1. Okay, so from the starting frequency up to the first corner frequency, what we have is the Bode plot, initial part of the Bode plot, correct? So what is the initial part formula? M is equal to minus 20n log omega plus 20 log k. So what is the value of n? 2. N is equal to 2 and k is equal to 1. N equal to 2 and k equal to 1. So n equal to 2 and k equal to 1 place kare. So what is the magnitude is minus 20 into 2 minus 40 log omega plus 20 log 1. Okay, plus 20 log 1. Log 1 is 0. The magnitude is just equal to minus 40 log omega. Okay, log 1 is 0. Initial slope, that means the initial slope, the slope of the initial part is minus 40 decibel per decade. Let me write down this magnitude for both the ends. For both the ends, 0.1 se 0.25 is the initial part, na? So omega equal to 0.1 starting frequency. So magnitude is minus 40 log of 0.1. Guys, that will come up as plus 40 decibel. And omega is equal to 0.25. Magnitude equal to minus 40 log 0.25. Log 0.25. That will come up as how much? That should come up as, I think, 24 decibel. Correct? Yeah. Just let me tally again. Yeah, absolutely correct. 24. Anjana, K is the K from the standard form, na? 2 into 0.25 and 0.5 got cancelled. Yes, good afternoon, Sai Tharun. Yes, Nikhil. Sorry, Nitesh. Nitesh, why we are taking the standard form? Otherwise, what is the value of K? You will read it as wrong. I told, just refer to the last class, why standard form is important. Without that, don't proceed. So magnitude is 40 and 24 at the ends of the initial part. Now, what is left in the calculation is the phase calculation. Gj omega Hj omega is 1 plus 4s, that is 1 plus 4j omega, divided by s square, that is j omega square, 1 plus s, 1 plus j omega, 1 plus 2s, so 1 plus 2j omega. Just written down the function here. Okay. So what is the phase? What is the phase formula? Let us write down the phase formula here. It is tan inverse numerator plus tan inverse 4 omega, denominator 2 times j omega, so 2 times 90, then tan inverse omega, tan inverse 2 omega, tan inverse 2 omega. Okay. Now let us calculate this phase at some frequencies. Example 0.1 starting frequency, first corner frequency 0.25, next corner frequency 0.5, next corner frequency 1, then let me randomly take it as 10 and then proceeding towards infinity. Can start calculating the phase at these points. Infinity पे क्या होगा? Infinity पे the phase is tan inverse infinity 90 minus 180 minus 90 minus 90, so it is minus 270, the final angle minus 270. Okay. Okay. All right. Now at omega equal to 0.1 and all, let me just calculate and put down the results. 0.1 is first now. First one is, yeah, correct, Shreya. It is coming up as minus 175.2 degree. Next one, now 0.25. Next is coming up as minus 175.6 degree. Very close, just very close. Then 0.5. Next is 188. Omega equal to 0.5 पे 188 degree. 188.1 approximately 188 लिख रहे हैं. Omega equal to 1. Minus 212. Minus 212 degree. 212.5 degree. Okay. Then randomly 10 is just a randomly chosen value. It can be anything and even not necessary even if you take that. This is coming up as minus 262.8 degree at 10. Finally going towards minus 270. Okay. And once again, in between minus 175 and minus 188, there goes the phase minus 180 degree. There goes the phase minus 180 degree. So in between 0.25 and 0.5, there will be somewhere omega p. Okay, let us not calculate it always. It is just some value omega p between 0.25 and 0.5. Okay. All right. Okay. Now let us go for sketching of the plot. Let us go for the sketching of the plot. Just take down these values. Okay, let us take down. Yes, Sai Tarun, the virtual calculator has the tan inverse term. The virtual calculator has the tan inverse term. Need not worry about that. The virtual calculator has the tan inverse term. Now guys, first of all, magnitude plot. First of all, magnitude plot. What are the starting frequencies? 0.1 and corner frequencies for 0.25. So let me start with the first frequency 0.1, the starting frequency. What is the magnitude at the starting frequency is known to us, that is 40. That is 40. So this is the first point. What is the initial slope? Initial slope is minus 40 because there are two poles at origin. Okay, so start a line. And what is the next magnitude? ये भी note कर लेते हैं 24. 24 at 0.25. Let me first make that magnitude as well. 24 approximately यहाँ पे हमने लिया, तो let me consider this as 24. Just keep on noticing the graph with me. This frequency, guys, is your first corner frequency. This is 0.25. The first corner frequency 0.25. Okay. Now, what is the initial slope? Initial slope we know is minus 40 decibel per decade. Minus 40 decibel per decade. Now, this is the corner frequency 0.25, and this 0.25 corner frequency is due to what? This is due to a zero. And what is the effect of zero? What is the effect of slope when a zero comes? Whether it is minus or plus. For a zero, it is plus 20. Okay. For zero, it is plus 20. So let us come to the plot once again. Let us come to the plot, and minus 40 is the current slope, and you will add plus 20. So that is minus 20. The slope will be added, and as I told you, if the slope is added, bend the line upwards. So suppose there was no corner frequency. Just suppose there was no corner frequency, then this line will go in the same direction. But now corner frequency coming, the line will bend upwards. Just change it upwards. Now, till what point it will go? For that exact calculation, we need one thing. It will go up to the next corner frequency. It will go in this form up to the next corner frequency. This will have a slope of minus 20. That is minus 40 plus 20. Okay, up to the next corner frequency. So let us first see what is the magnitude at the next corner frequency and then join the points. So what is the next corner frequency in sequence, guys? The next corner frequency is 0.5. 0.5. So what is the magnitude at 0.5? How do you calculate the magnitude? Using that same slope methods. So here I am calculating the magnitude at the next corner frequency, that is 0.5. Okay, and that is given by slope. Slope of this line is minus 20. Slope of the new line is minus 20 is equal to magnitude minus m2 minus m1. What is the magnitude it is starting with? 24 divided by log of omega 2. Log of 0.5 tak jana hai. Minus what is the frequency that it is starting with? Log 0.25. This one. So we have to solve this. And solving this, you get the value of m is equal to, this is log 2. So minus 20 log 0.5 by 0.25 is log 2 plus 24. 20 log 2 is 6. So minus 6 plus 24 is 18 dB. Okay. Yes, I'm approximately correct. It is 18 dB. Remember, 20 log 2 is directly 6. So 18 dB. Magnitude at 0.5 is 18 dB. So I will come back to the plot to highlight this. 18 dB. So this was my 20 and this is somewhere 18. This is my 18 line. Okay, so let us join the points now. And this represents the frequency. This represents the next corner frequency of 0.5. See this one, 0.5. Now, this is the corner frequency due to a pole. See, the next two corner frequencies, 0.5 and 1, these are the corner frequency of poles, and because of the pole, the slope will now change by minus 20 in negative. So, this line had a slope of minus 20 dB per decade, and now minus 20, the new line will have the slope of minus 40. Will have the slope of minus 40. And again, if again I say that suppose there was no corner frequency, it will go in this direction, but it will again bend downwards. It will again bend downwards. Okay, it will bend downwards. Minus 40. So this slope will be minus 40. But again, the point is ki up till where I should extend it. This will go towards the next corner frequency, that is 1. So what is the magnitude at the next corner frequency? What is the magnitude at the next corner frequency? Guys, next calculation now. What is the magnitude at omega equal to 1? So that is minus 40. Now the slope of the line is minus 40. This new slope is minus 40. The changed slope is equal to m2 minus, it is starting with 18 magnitude, divided by log of 1 minus log of 0.5. Okay. So m will be equal to minus 40 log 1 upon 0.5 is again log 2 plus 18. 40 log 2 will be minus 12. So this magnitude is coming as 6 dB. Yes, Abhishek, initial slope by the initial formula. Yeah, directly number of poles of GSHS at origin. Number of poles of GSHS at origin. Okay. Yes, Nitesh, I told corner frequency is the frequency where slope change will occur. Or corner frequency is the frequency where two straight lines or two asymptotes are joined. Two asymptotes intersect. Okay. Okay, Nitesh. So this will go towards the magnitude equal to 6. This is 10. Let's take this is 6. Yes, Abhishek, number of poles of GSHS at origin. Yes. So this line which I was sketching, this will go till 6 decibel at omega equal to 1. Just a second. At omega equal to 1. This is omega equal to 1. And what is the slope of this line is minus 40 decibel per decade. And guys, once again comes a pole. And because this is a pole, the slope will again change by minus 20. So minus 40 minus 20. The new slope will be minus 60. Matlab just bend it downwards. Just bend it downwards. Without the corner frequency, this was the normal shape, but now I will bend it downwards. Just bend it downwards, and this line will have a slope of minus 60 decibel per decade. Minus 60 decibel per decade. Okay. Yes, that completes my magnitude plot, because thereafter there is no slope change. After this, there is no slope change because there is no more corner frequency. Because there is no more corner frequency, so there is no more slope change now. Right? There is no more slope change now. Slope changes occur only at the corner frequency. So this will go till infinity. This will go till infinity. This is the complete magnitude plot. This is the complete magnitude plot. Okay. Next is, let us also represent the phase plot in this plot. Let us also represent the phase calculations. Already it is done. We have completed the phase calculation already. Already we have just gone through it. Just as I told in the previous case, there is just an alternate axis taken to define the values of the phase. Just an alternate axis taken to define the values of the phase. Define the values of the phase. This is phase to be represented in degrees. Okay, what is the phase on the x-axis? It is taken as minus 180 degree. Oh yes, I was supposed to tell you why we take the phase as minus 180 degree, right? Why we don't take the phase as 0, starting 0 nahi leke minus 180. Why it is so? I was supposed to tell that. So come to the previous Bode plot which is completed. See, Bode plots. One of the main use of the Bode plot is to do the relative stability analysis. That is the analysis of gain margin and phase margin. Okay. Gain margin is calculated at omega p, phase margin at omega g. Omega g is the frequency as we have calculated, as I have shown you also. Omega g is the frequency. We calculated, na? Yeah. Omega g is the frequency at which the magnitude is 0 dB. Actually 1, absolute value 1, but in the magnitude 0 dB. Okay, 0 dB matlab x-axis. So where do we find the omega g? Where do we find the omega g? On the x-axis, on the 0 dB line? Okay. Now suppose, listen guys, suppose if I had taken this as 0 degree. Suppose. So where will be minus 180? Where will be minus 180? It will be somewhere downwards, obviously, below the x-axis, negative value of y. So now you want to calculate omega p. Now you are interested in calculating omega p. Omega p is the frequency at which the phase is minus 180. So now you will see where is my phase minus 180 and where does my phase plot cuts this axis. So you will have to look into the values into two different axes. Omega g x-axis pe milega. Omega p you will be obtaining on some other axis. Omega p you will be obtaining on some other axis, this one. Okay. So just to get a common axis for both, because as I told, one of the important reasons of studying Bode plots is the stability analysis that is based on omega p and omega g, and I am interested in looking into omega g, omega p on a same axis. On a same axis. ठीक है, तो इससे clear idea होता है who comes first. Omega g comes first, okay, this is stable. If omega g comes second, that is unstable. We know the relations between omega g, omega p for stability. Okay, so that is why on the x-axis where magnitude is 0, there only the phase should be 180 degree, minus 180 degree. It should not be 0. That is why we don't take it as 0. I hope the reason is clear. Okay. Yeah. Now let's come back to the current Bode plot. This is what. I hope the reasons are clear to you guys. So that we find omega p, omega g on the same level, on the same axis. Okay. Now this is minus 180 degree. Again, for simplicity, let's take the 30 degree case. Minus 210, minus 240, minus 270. Last angle is minus 270, minus 150, minus 120. Okay. Now let's take the phase plot. Let us take the phase plot. Phase calculations are there. Minus 175.2, minus 175.6, then minus 188. So minus 175.2 and minus 175.6 are both almost close to 180. So just let me take it, start from here. मैंने बोला था ना, this is the only y-axis. Only thing, readings are shown on the right side, but this is the y-axis. Okay, and if this is the y-axis, at 0.25 also the phase is approximately 175 only, nearly the same value. Then at omega equal to 0.5, it has minus 188. Minus 188, below minus 180. Somewhere below minus 180. This will be the next value of phase. Then omega equal to 1 pe, it is minus 212. Somewhere this. Then omega equal to 10, it increases to minus 262 and then finally take towards minus 270. So just freehand drawing, just join these points approximately. Such that you finally go towards minus 270 degree. This is my phase plot. Okay, on the same plane, this is my same plot. This was my frequency 0.5. I will write it here. Okay, and something else I erased. Yes, I will write down the slope of this line here. The slope of this line is minus 60 decibel per decade. Minus 60 decibel per decade. That completes my Bode plot. Now, stable or unstable, that you will tell me. I don't want the answers, that you can calculate separately. I just want to see whether stable or unstable. Whether it is stable or unstable, what you have understood. So just I will highlight omega p and omega g. See, what is this? The phase is minus 180 degree. So this represents the omega p. Okay. What is this? The magnitude is 0 dB. So this is omega g. This is omega g. Omega g is greater than omega p. So unstable. It is clearly unstable. Acha, what about the phase margin and gain margin? Look at this. Gain margin is calculated at omega p. Now guys, listen. Gain margin is calculated at omega p. So I will highlight the gain and phase margin also. Look at this. Here. Let's calculate the magnitude at omega p. The gain margin is equal to minus of this m. Suppose this magnitude is minus. I told the gain margin is the negative of the magnitude reading obtained from the Bode plot at omega p. So this is my omega p. What is the magnitude at omega p? It is positive, and then when you take minus sign, it is going to be negative. Okay. Then phase margin is calculated at omega g. Okay, so this difference, this omega g and the phase at this point. See, the magnitude of the phase at this point is greater than 180 degree. The 180 degree plus this one, answer is going to be negative. This gap is your phase margin, will be negative. Gain margin will also be negative. Gain margin will be negative. Okay, omega p less than omega g. I will just write down here. Just a second. Just need to add a slide. I'll just write down here. Omega g is less than omega p. Sorry, greater than omega p. है ना यहाँ पे? Omega g is coming next. Omega g greater than omega p. System is unstable. Okay. The gain margin is negative of m, but the m is positive. So gain margin is overall negative, unstable. Phase margin is also negative, unstable. Calculations I explained with the last question. Okay, rest is up to you, homework. Because we need to concentrate, after some time we need to concentrate more on the MCQ question. So let us not repeat the same question that I am giving you as homework. Determine omega p, omega g, gain margin, phase margin. Nitesh, just now I explained कि why we take the phase as minus 180, and because this is minus 180 तो ऊपर जाओगे तो पहले negative ही आएगा ना, somewhere here ऊपर जाते जाते then you will get 0 and above that it will be positive. And why I start from minus 80, just now I explained that. No, Anjana, not to take, no. Not to take 20 log again, because the magnitude that you have sketched on the Bode plot is already in the form of log. 20 log. ठीक है. So minus of magnitude, this is positive. So minus of positive will be minus. Okay. Now guys, screenshot for this one. Screenshot for this question quickly. Let's take the screenshot for this question. Next one. Next. Next one. Next. Next one. Next one, the final Bode plot. The calculations. Next one. Okay. Okay guys, now understand the next concept, that is the minimum and non-minimum phase systems. The minimum and the non-minimum phase systems. Minimum and non-minimum phase systems. Now to make you understand the concept, see, final conclusion for minimum and non-minimum phase system, that is just with respect to location of poles and zeros. That is very simple. But what is the concept of minimum phase and non-minimum phase? Let us understand the concept first. Okay, and for that, consider following two transfer functions: 1 plus 2s upon 1 plus s, 1 minus 2s upon 1 plus s. Okay, just understand the calculation of these two. G1 j omega is 1 plus 2 j omega upon 1 plus omega. G2 j omega, 1 minus 2s means 1 minus 2 j omega divided by 1 plus j omega. So in the complex form, it is a difference of conjugate. This is x plus jy and this is x minus jy. What is the magnitude of this? What is the magnitude of this? Root over 1 plus 4 omega square divided by root over 1 plus omega square. And what is the magnitude here is root over, again, whether it is x minus jy, after getting the square, minus 2 omega square is again plus 4 omega square divided by under root 1 plus omega square. The first point to be noted is that the magnitude of both the functions are same. Okay, the magnitudes of both the functions are same. So if I try to take the Bode plot of them, Bode magnitude plot, first I am taking only the Bode magnitude plot, it will be same. The Bode magnitude plot will be same for both. So this is, suppose, the magnitude in decibel. This is your log omega axis. Okay. Why it is same for both? Because the magnitude functions are same. What are the corner frequencies? In short, I am solving this Bode plot problem. The corner frequencies are omega equal to 1 by 2 and 1. This is due to the 0 and the 1 is due to the pole. I've written it like this. 1 is due to the 0, 1 is due to the pole. Okay, so just see my Bode plot. Approximately, finally, point 1 is my starting frequency. Less than 1 by 2 and 1. So point 1. Okay. Also, what is my initial part? My initial part is given by the formula minus 20 n log omega plus 20 log k. Okay, so what will be initial part? N ka value kitna hai? What is the value of n? Number of poles at origin is 0. What is the value of k? K is 1. K matlab there is no constant multiplied separately. So means k is 1. So overall k is 1. Log 1 is also 0. So magnitude is 0. Initial magnitude will be just 0 only. Matlab lying on the x-axis only the Bode plot will start. Okay, and then you have to wait for the first corner frequency. So here comes the first corner frequency, which is 0.5. Here comes the first corner frequency, which is 0.5. That is due to a 0. So slope will change in positive. Slope will change by positive. So slope becomes plus 20 decibel per decade. Then you have to wait for the other pole to come. That is 1, and here the slope will again change by minus 20. So already this slope is plus 20 minus 20, slope will now become 0, and 0 slope means parallel to the x-axis. From this point, now take a line parallel to the x-axis. This will have 0 slope, parallel to the x-axis. Okay, this is the magnitude plot. Okay, for both the systems. So I have two systems, both of them having the same magnitude plot, because Bode plot, even if you take the actual magnitude plot, the function is same. So there is no difference absolutely. Okay. All right. Now, this is about the magnitude. I hope you have got it. Now, coming to the important term. As you see that the name is minimum and non-minimum phase. So, it has to do something with the phase. So, now going for the phase 1. Okay. Yes, the position of 0 will matter, Zayed. That's what. That is the important point here. The position of 0 will matter. And to explain that position first, let me take the phase. So what is phi 1 j omega for the first function? Phi 1 j omega. Write down the phase function of this, tan inverse omega, tan inverse 2 omega numerator, denominator mein phase tan inverse omega. So subtract tan inverse 2 omega minus tan inverse omega. Phi 2 j omega. Tan inverse. Now numerator x minus jy, fourth quadrant. X minus jy. So minus 2 omega by 1 minus y by x. Tan inverse minus y by x. Minus tan inverse. Denominator is the same. So tan inverse omega. But numerator was not same. So phase will not be the same for both the functions. Tan inverse minus y by x. Fourth quadrant formula, guys. I've told you. Fourth quadrant formula is minus tan inverse y by x. Minus tan inverse y by x. Okay. Now look at this table with me. Just follow this table with me. I take some values of omega because phase is important to going for the actual phase analysis. In the next class, I will tell you the approximate phase analysis also. Then calculating the phi 1. Let's take only mod of phi 1. Angle plus or minus, angle plus or minus, it is just about anti-clockwise or clockwise. Now I'm taking mod phi 1 and mod phi 2 values. Okay. And let's take some values of omega. Suppose 0 degree. Then 0.1, the starting frequency of the magnitude response. 0.5, 1 degree. And then take it towards infinity. Increase karte, what are the results? Let me write down those results here. Let me just write down those results here. Okay. For the first one, tan inverse 2 omega minus tan inverse omega. For the first frequency, 0. So tan inverse 0 minus 0, that is just 0. Okay, for the second one, 0.1 के लिए calculate करते हैं, tan inverse 0.2 minus tan inverse 0.1. Okay, that is coming as 5.59. So 5.6 लिखते हैं approximately. For you, not necessary to calculate, just understand here. The next is 0.5. So that is straight away 45 minus tan inverse 0.5. Here I am getting as 18.43. 18.43. ठीक है. Then 1 लिया हमने, तो tan inverse 2 minus 45 degree, and that is again 18.43. And infinity, tan inverse infinity minus tan inverse infinity, 90 minus 90, 0. Then phi 2 mod के फॉर्म में एक्चुअली नेगेटिव आएगा, तो फर्स्ट विल बी 0 ओनली, tan inverse 0, tan inverse 0, that is same as 0 degree, that is same. Next is 0.1 पे, तो tan inverse 0.2, tan inverse 0.1. This is coming up as 17 degrees. This is coming up as 17 degrees. After taking the mod, it is actually minus 17, taken the mod. Okay. Then 0.5 पे, 71, 0.56 degrees. Then 1 पे, 108, 0.43 degrees. And infinity पे tan inverse infinity, तो minus 90 minus 90 is minus 180. So after taking mod, it is plus 180 degree. It is plus 180 degree. Correct. Now, for both of the system, guys, for both of the system, let us have the plot versus omega. Let us have the plot versus omega. Phase in degrees versus omega. Normal omega, no logarithm thing here. Okay. Can you say, look into the table and say that which of the phase values are always lower as compared to the other one? Which of them is always lower as compared to the other one? Which of them always lower as compared to the other one? Can you say that? Yes, guys. The first one is always lower than the second one. The first one is always lower than the second one. Okay. Now, what is the nature of the graph of the first one? Just follow with me. It starts from 0 degree. Okay. See, it starts from 0 degree, 0, 5.6, 18 and again 18. 0.5 and 1 पे 18 and 18 same. मतलब what is the nature of this? This is actually again a type of compensator. So actual phase calculation, what is maximum phase, how to sketch the plot, I will tell you with compensator again. But here I'll just tell you the approximate shape of this graph. At omega equal to 0.5 and at omega equal to 1, the phase values obtained are same. The phase values obtained are same, and that is 18 and 18 degree. 18 and 18. That means the function was first 0, then 0 say it increases to 5.6, it increases to 18, it increases to 18 degree, and again after some frequency it is 18. That means what? That means what? The phase might be increasing and then it reaches a maxima and then decreases. Okay. Now, what is this maxima? This is important, but this is important in compensators. I will discuss this again in the compensator. But right now, this is my phase plot for the phi 1. For the phi 1. Okay. This represents the phase plot for the phi 1, mod phi 1. Okay. And then the second one, where the phase values are always greater than the first one. And it is going to go towards 180 degree finally. It is going to go towards 180 degree finally at the end of the day. It's going to travel towards 180 degree. And so what is the approximate phase plot? Just a freehand sketch I'm using here. It rises, starts from 0 only, but see at 0.5 it has become already 71 degree. So it is increasing rapidly, and it increases, and finally it tends towards 180 degree. This is the representation of mod of phi 2. Okay, mod of phi 2. Okay, that means what? That leads to a simple conclusion that mod phi 1 is always lower, or we can say minimum, as compared to mod phi 2. Guys, I am trying to compare the phase of two systems. Now listen, I am trying to compare the phase of two systems, but to compare the phase of two systems, firstly I have taken two systems having the same magnitude response, as we have considered. The phase of two systems are compared considering they are equal on the magnitude scale, but they are differing on the phase scale. Okay, that is what. Consider two systems having the same magnitude response. Now, how the comparison is done using the same magnitude response. The system having the lower values of phase, for all frequencies is said to be having minimum phase as compared to the other system, is said to be a minimum phase system. This system, which means which one? Which one is minimum phase here? The first one. The first one is said to be minimum phase, right? I'll just write down one more point here. So if I take the first one again, G1s, that was 1 plus 2s by 1 plus s, and G2s. Now conclusion. Coming towards conclusion. Actually, अगर question में आपको identify करना है, तो how to identify? The actual concept is a comparative concept. Okay, that is why I took the concept first, and then conclusion is simple. Okay, what is the pole zero plot of the first one, and what is the pole zero plot of the second one? What is the pole zero plot of the first one? What is the pole zero plot for the second one? Just sketching that quickly, roughly, for the first and the second. Okay, for first, what is the 0? 0 is at minus 1 by 2, and the pole is at minus 1. For the second one, the 0 is actually plus 1 by 2, and the pole is at minus 1. And whenever there is a 0 or even a pole in the RHP, then the system is non-minimum phase. And vice versa, if all the poles and zeros are in the left half plane, then the system is a minimum phase system. That is the final conclusion. Okay. Now, Nihar, overall stability of the function is dependent on the poles of the system, not the zeros. Okay. That is why I didn't take the pole in the RHP. So if all the poles and zeros of a function are in LHP, then it is a minimum phase function. And if some poles or zeros, whatever, in the RHP, then it is a non-minimum phase system. Okay. Yes, Anjana, even if RHP pole is there, suppose, let me write down that example. Suppose if I had taken the example G2s as 1 plus 2s upon 1 minus s. 1 plus 2s. Here it was 1 minus s upon 1 plus s. If I take 1 plus 2s upon 1 minus s, that is also a non-minimum phase system. But why I didn't consider? Because actually the system itself becomes unstable, so no need to analyze the unstable system. But mathematically speaking about minimum and non-minimum phase only, this will be non-minimum. For minimum phase, all the poles and zeros in LHP, and even if a single pole or zero is in the RHP, that is said to be non-minimum phase. Okay, that is said to be non-minimum phase. Away from the origin, but where, Amit? Away from the origin, but in which side? All right. Yes, there's one more thing I want to discuss. That is the all-pass systems. Simple thing that you study once again in the signals also, because there you study about frequency domain analysis a lot. Signal systems is mostly on the frequency domain analysis, the Fourier transform part especially. On the real axis LHP, yeah, matlab, see Amit, if all the poles and zeros are in LHP, whether they are close to origin or away from the origin, it is a minimum phase system. Only thing is, if they are away from the origin, then such poles are indominant, they can be neglected. But still the system is minimum phase only. Okay. Yes, all pass systems. All pass systems. And all pass system is one which passes all the frequencies with equal gain. Which passes all the frequency with equal gain. Okay. No, Lasya. Sorry. Omega is not in degree ना. Maybe in Hari Bari I wrote. Omega पे degree कैसे आएगा ना? No, Lasya. Okay. So it's not in degree. Phase is in degrees. All right. An all pass system is one which passes every frequency with equal gain. This is not the case with all systems. Already we have done the frequency. Just let me take that example. Already we have done the frequency response analysis. Already we have done the frequency response analysis of first order and second order in the earlier classes, in the resonance class, if you remember. We were talking about the frequency response analysis of first and second order. Suppose if I take the first order case only. Suppose if I take up the first order case. Suppose you have the transfer function of the form 1 upon 1 plus 2s. Yeah, simply 1 upon 1 plus s. Okay, that means what is the frequency function? Frequency response. Frequency response will be 1 upon 1 plus j omega. And then what is the magnitude? It is given by 1 upon under root 1 plus omega square. And then we know that. Guys, this again I have told you in the frequency domain class number 1. Suppose to this system, if you apply a input 2 sine 3t, if you apply a input to the system 2 sine 3t, the output is, I have told you in the response to sinusoids frequency domain class, the output will be 2 into the magnitude of the frequency response, that is 1 upon under root 1 plus 2 square. The frequency 3 square into sine of 3t plus the phase. That is anything. Let that phase be anything. Okay, but the output gain, the output amplitude will be 2 divided by root 10 into sine of 3t plus 5. Okay, what if I change the frequency to 4t? If this is 4t, here also you will write down 4, correct? Okay, and then the amplitude of oscillation will be 2 by root 17. Okay. That means the output amplitude, obviously the output amplitude depends on the system gain, and the system gain is dependent on omega. System gain is dependent on omega. Okay, so every frequency will be passed by different gain. Every frequency will be passed by different gain. Okay, we have done the similar analysis for second order also, and there we calculated the resonant peak and resonant frequency. Concept क्या था resonant peak, resonant frequency का? Resonant peak is the frequency at which you obtain the maximum amplitude of oscillation, because the output is oscillating but at different amplitude for different frequency. Okay. But now this is all discussed in resonance, where the amplitude is a function of omega. But now I am trying to talk about a special case, such a system which passes every magnitude, every frequency with equal gain, and that is possible. That is only possible if the mod of tj omega is constant, independent of frequency. Actually, it can be any constant, but that is you know as a convention commonly it is taken as 1 ideally. Okay. An all pass system is one which passes all frequencies with equal gain. Okay, that means magnitude should be constant for all frequency, and that magnitude is usually taken as 1. Okay, although even if you take a system of the form, suppose it's a system where mod tj omega is equal to 2, that is also constant magnitude, that is also all pass, but commonly it is taken as 1. So talk about a system where mod tj omega equal to 1, and one of the example is written in front of you. If you take it in the frequency domain, tj omega 1 minus j omega t upon 1 plus j omega t, and then calculate its magnitude mod of tj omega. It is under root of 1 plus omega square t square, because conjugate से फर्क नहीं पड़ेगा ना. X minus jy also has the magnitude root over x square plus y square. Denominator root over 1 plus omega square t square. Basically they are same. Mod of tj omega equal to 1. Basically they are the same, and mod of tj omega is equal to 1. The mod of tj omega is equal to 1. Alright. The mod of tj omega is equal to 1 for all omega. Matlab there is no dependency on the omega, and it is cancelled out for all omega. Okay, it is constant, and such a system is an all pass system. Such a system is an all pass system. Okay. Such a system is an all pass system. And what about the pole zero diagram of this? What about the pole zero diagram of this? Ts is 1 minus st by 1 plus st. Okay. Can you say some property about the pole and zero? Sketch तो हम सभी कर लेंगे. What is the property of pole and zero here? What is the property of the pole and zero here? The zero is located at s is equal to 1 by t. The pole is located at s is equal to minus 1 by t. Yes, guys, can you say any property? Sketching and all that will be done. Yeah, it is non-minimum phase. That is correct. It is a category of non-minimum phase. Apart from that, any special property? Yes. Yes, the special property is symmetry. It is symmetrical with respect to the y-axis. Yeah, with respect to the origin also you can say the zero. Sorry, I've correct. The pole is at minus 1 by t, and the zero is at plus 1 by t. That plus 1 by t. Symmetric. Same distance from origins are correct. Okay. The poles and zeros are symmetric about the omega, about the j omega axis. Okay. Now, an all pass system will always have symmetric poles and zeros. An all pass system will always have symmetric poles and zeros. So look at this example. Now this is a second order example. Earlier was only first order, one pole was there. Now two poles. So corresponding to the two poles, two symmetric zeros are there. Corresponding to the two poles, two symmetric zeros are there. This is also an example of all pass. This is also an all pass system. Okay. This is also an all pass system, guys. Correct? This is also an all pass system. Because if you try to sketch the poles and zeros, it is symmetric. If you sketch the poles and zeros of this, that will be just symmetric. Okay, so it will always be non-minimum phase only because of symmetry. If pole is on left, the zero will always be on the right, and it is symmetric. The poles and zeros are symmetric with respect to the imaginary axis. Okay, with respect to the imaginary axis, they are symmetric. All right, guys. Now, one more thing, just because I've introduced all pass system now, what will be the polar plot of this? What will be the polar plot of an all pass system? Can we do it? What is the polar plot of an all pass system? See, here there is no starting and diving angle applicable, because I told now you have to be careful when n is equal to 0 and p equal to z. N is 0 and p is equal to z. Can you try it out quickly? T of j omega is 1 minus j omega t divided by 1 plus j omega t. Okay, so first of all, what is the magnitude? Magnitude means mod of t j omega, polar plot, and that is just 1 because it is all pass. Root over 1 plus omega square t square and divided by root over 1 plus omega square t square. Phase is tan inverse minus omega t minus tan inverse omega t. Tan inverse minus y by x. X is just 1. So minus tan inverse y by x. So overall it is minus 2 tan inverse omega t. Yes, correct, Anjana. At omega equal to 0 plus starting frequency I am calculating separately. No need for starting and diving angle here because the magnitude will be finite. There will not be any diving into the origin. Magnitude is constant 1. Phase will be 0 degree. Okay. Omega equal to infinity plus magnitude is always 1. The phase will be minus 2 tan inverse infinity and that is minus 180 degree. That is equal to minus 180 degree, right? Minus 180 degree. The phase is minus 180 degree. Okay, done. Okay, so this is the phase. Now, only by the 0 plus and infinity plus approximately the shape should come up. Approximately the shape will come up because magnitude is always 1. So magnitude means distance from origin. So it is going to be in the form of a unit circle. It's going to be in the form of unit circle. This point is 0 plus phase 0 degree, matlab positive x axis. Phase 0 degree, positive x axis. Phase 180 degree, negative x axis. So this is infinity plus. This is infinity plus. This is infinity plus. Okay. Arrows are from 0 to infinity. It's basically a unit circle because magnitude is fixed 1. The distance from origin, it is fixed as 1. So it takes the shape of unit circle. The distance from origin is always 1, like radius equal to constant. Okay. All right, guys. Now time to take the screenshots. I think we have not taken from the minimum phase only, na? Correct. Minimum phase से ही शायद नहीं लिया as far as I remember. Then start taking from the minimum and non-minimum phase, and then we move towards the next topic. Minimum phase, non-minimum phase. Next one, I'll hide my view. Next screenshot. Next. Next. No, Zion, it is actually, can't say because it is indeterminate. It is any frequency actually. Last year, if you're asking with respect to this minimum phase, non-minimum phase, yes, I took the x-axis directly as omega, not log omega, because my main concern was minimum phase and non-minimum phase. As the word says, we are talking about phase. So I wanted the actual phase analysis of the system. Okay. Actual phase analysis of the system, not on the log scale, but on the normal y versus x graph. Next screenshot. The concept of minimum and non-minimum phase is about the phase only. So we were trying to do the actual phase analysis of the system. Yes, guys. Next screenshot. Next one. Next. Next one. The next. 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 All right. So if you remember, till now we have done the Bode plot analysis for the constant term k, for poles at origin, for 1 plus st, for 1 upon 1 plus st. Okay. And as I told, next we are looking into e power minus st. Next, after that, I will discuss the second order system. Okay. And after that, I will discuss the asymptotic phase plot, the approximate phase plots, and then we will jump to our MCQ questions, the gate level problems. Okay, that will be very interesting, that will be fun, and that is easy to solve. Okay, so e power minus st second order and the phase approximations I will tell, and then we have the gate questions. Then we move towards the gate questions. Okay, all right. So I'm starting now with the e raised to the power minus st. Starting with the e power minus st. It's a very simple case, no much complications here. So what is gj omega? Hj omega is e raised to the power minus j omega t. Okay, e raised to the power minus j omega t. So what is the magnitude? Now Bode plot की बात कर रहे हैं तो magnitude is obviously 20 log mod gj omega Hj omega, and that is equal to 20 log mod of e power minus j omega t. And as already discussed, what is mod of e power j theta? That is always 1 cos theta plus j sin theta. So 20 log 1, and magnitude is 0 dB. So there is no magnitude effect of this term. In decibel it is 0 dB. Okay, so magnitude is 0 dB. Then what about the phase of this term? The phase e power j theta. The phase is theta, right? The phase is minus omega t. But when you write theta from the Euler form, it is in the form of radian. But in the Bode plot, we want the phase as. In the Bode plot, we want the phase as degrees. The standard unit of phase in Bode plot is degrees. So minus omega t into same conversion I've told you. 57.3. This we have used multiple times. Now 57.3 degrees. 57.3 degrees. Okay. Can you just guess? Can you just guess कि when I take the Bode plot of this, what should be the shape of the phase plot? In the Bode plot, magnitude is just 0. Magnitude is just 0. What should be the shape of the phase plot? Magnitude is just 0. Okay. Yeah, can anyone say what should be the shape of the phase plot on this Bode one? No, Zion, not linear. No, Verma, it's not linear. See, maybe you are telling linear, maybe because you are saying omega is here, so y equal to mx. All this is just a constant t into 57.3, but that is not the correct way because on the Bode plot, this is not omega axis, this is log omega axis. This is log omega axis. Okay, so in Bode plot, the x-axis actually is log omega. So what is omega actually? omega is 10 raised to the power x. Yes, it is going to be exponential actually, Amit. See, phase on the y-axis, y is equal to minus omega into some constant. Let that constant be k. K 10 raised to the power x. Like e power x. Okay, it's an exponential graph, 10 power x, where the base is 10. It's an exponential type of graph, but with a minus sign. Exponential increases this way. Okay, minus matlab it is on the negative y-axis. It is towards the negative y-axis side, and the phase plot, I'm going to represent it now. The phase plot will be something of this form. Okay, I'm taking some lower value of phase because starting frequency मैंने बोला है ना, starting frequency is never taken as zero in Bode. So what is the starting frequency? That depends on question to question. So based on the starting frequency, there will be some starting phase and it decreases. Actually, this is the exponential graph. I'm taking for the negative y-axis, so going towards minus infinity. Okay, and this is my phase plot. My phase plot. Okay. So this is the Bode plot analysis of e power minus st term. For the e raised to the power minus st term. This is the Bode plot analysis, right? Screenshot. Time for quick screenshot of this one. Next. Next one. Now, giving you one homework activity. Already I have explained you how to sketch Bode plots. Okay, in the conventional manner, sketch it in the conventional manner so that you get more clarity. Okay. So sketch it in the conventional manner, like step by step, like we done for the previous problems. Okay, so sketch this Bode plot, including the exponential term. Give you one homework question. Okay, chaliye. So the last one quickly. GSHS, this is also very simple. GSHS equal to omega n square upon s square plus 2 zeta omega ns plus omega n square. So for this, let us first write down gj omega hj omega function. Gj omega hj omega function as omega n square divided by j omega whole square plus 2 zeta omega n s j omega plus omega n square. Okay, that is basically omega n square upon what is the real part in the denominator, omega n square minus omega square plus j 2 zeta omega n omega. Okay, now divide by omega n square. Divide by omega n square. So what do you get? Dividing by omega n square, you get gj omega hj omega as 1 divided by, dividing by omega n square, 1 divided by 1 minus omega square upon omega n square plus j 2 zeta. Now dividing by omega n square, so one of the omega n will cancel. I get omega by omega n. Omega upon omega n is coming together. So now guys, what is the magnitude of this? What is the magnitude of this? Okay, first let me write down what is the face of this. Face is simply minus tan inverse y by x 2 zeta omega by omega n divided by 1 minus omega square by omega n square, or I can multiply here by omega n square. it is minus tan inverse of 2 zeta omega omega n upon omega n square minus omega square. फेज प्लॉट्स अभी तक हमने फेज पे कोई अप्रोक्सीमेशन नहीं लिया है, तो फॉर दिस विल टेक द डायरेक्ट प्लॉट. व्हाट अबाउट द मैग्नीट्यूड? सी मैग्नीट्यूड इज मतलब लॉग, बोडे प्लॉट की बात कर रहे हैं तो ऑब्वियसली आई टेक 20 log 20 log. What is the magnitude? Numerator is just 1. Denominator magnitude, write down root over x square plus y square. 1 upon root over x square. 1 minus omega square by omega n square का whole square. X square plus y square. Plus y square. That is 2 zeta omega upon omega n whole square. Log 1 by x is minus log x. So magnitude is minus 20 log of root over 1 minus omega square upon omega n square the whole square plus 2 zeta omega upon omega n whole square. ठीक है? Okay. Now, what are the approximation? Now, starting with the approximation, guys. First case, if omega upon omega n is less than 1, that means omega is less than omega n. That means talking about low frequencies. So, magnitude will be equal to, look at this. Omega by omega n is less than 1. So square करने पे it is much more less than 1. So it is neglected in front of 1. Same approximation, something like same that we did for the first order. So it is approximately under root of 1 minus, this is cancelled. Okay, this is like very small, to take it cancelled to 1 square plus. Now again this is omega by omega n whole square. This is also neglected. So overall what is left is just 1. So magnitude is approximately minus 20 log of root 1. Root 1 is 1. 20 log 1 is 0 dB. Okay. Second case, omega upon omega n is greater than 1, which means omega greater than omega n. Omega is greater than omega n. That means now we are talking about high frequency. So what will be the magnitude now? Approximately, look at this. Now omega by omega n is much high. So सबसे पहले तो 1 will be neglected. So what you get? Minus of omega square by omega n square whole square. Minus gets cancelled by square. So omega power 4 by omega n power 4. And what is here? This will be 4 zeta square omega square by omega n square. Okay, so this is power 2 and this is power 4. Okay, where condition is omega by omega n is much greater than 1. Suppose a is much greater than 1. Okay. Suppose a is much greater than 1. Yugandhar, let's take zeta for underdamped. Let us take it as for underdamped right now. So if a is greater than 1, suppose if a is equal to 10,000. That is basically 10 raised to the power 4. So what is a square? A square is 10 power 8. But what is a power 4? What is a power 4? Is 10 raised to the power 16. Understand it is like this. A square is 10 power 8. A power 4 is 10 power 16. And 10 power 16, see, although 10 power 8 is also big, but it is nothing in front of 10 power 16. It is nothing in front of 10 power 16. So 10 power 16 plus 10 power 8. 10 power 16 में 16 zeros आएगा. Even if you add this, it can approximately be written as 10 power 8 only. Comparatively, it is a negligible term. That means if a is greater than 1, a raised to the power 4 will be much greater than a square, and hence this can be neglected. That is what I am going to use here. This is a square term, this is fourth power term. The fourth power term will be dominant. I hope this is clear to you. Just remove this rough calculation. So only taking the fourth power term approximately. Okay. So magnitude is approximately equal to minus 20 log under root of omega power 4 by omega n power 4. Rest all just gone away. ठीक है. तो yes, not only minus 40 log omega, omega by omega n. ठीक है, अंडर रूट और पावर 4 कैंसिल हो गए, पावर 2 बचेगा, टेक द पावर 2 आउटसाइड, तो इट इज minus 40 log omega upon omega n, minus 40 log omega upon omega m, or the magnitude is minus 40 log omega plus 40 log omega n, because log of a by b is log a minus log b. Now this is y, and we know log omega matlab x axis, so y it is minus 40x plus some constant. So once again you get, for high frequency also you get a straight line with a slope equal to minus 40 decibel per decade. Minus 40 decibel per decade. And guys, now listen, what is my approximation? What is my approximation? Approximation is similar to what you have learned for first order. Okay, what you have learned for first order, that when omega is just less than the corner frequency, we take it as zero frequency, and it is greater than the corner frequency, we directly take the straight line, something like that. Okay, although we have derived the result for omega less than omega n, but omega, if it is even slightly less than omega n, the magnitude will be approximated by the low frequency. Okay, just try to recall the first class, need not repeat every point. Yes, exactly, it is going to be defined as corner frequencies, Ian. Okay, so need not repeat our whole definition, all definitions and all done there. Okay, only thing is we took omega less than omega n. मैं क्या बोल रहा हूँ, omega if it is even just small than omega n, less than omega n, we will take the magnitude as 0. Okay, if it is greater than omega n, we will take the magnitude defined by this straight line, and this straight line has a negative slope minus 40 decibel per decade. Okay, and then under such a context, this omega n, this should be named as what? This is named as corner frequency, the frequency which connects two straight lines, the frequency which connect two asymptotes. The frequency which connect two asymptotes. Achha, why it is asymptote? You want to know that also? Omega n is corner frequency. Look at this. Look at this proper MATLAB graph and understand the analysis. This blue dotted one, ये जो आप देख रहे हैं ना, ये वाला, just follow this. This blue dotted line is that straight line plot जो मैंने अभी sketch किया, the last slide. This is the copy of that. Straight line up to the corner frequency it is 0, and up after the corner frequency it has a slope of minus 40. So it is that same thing. Okay, but what is there with the other lines like this green line, red line, yellow line, and the blue line? If you remember why these plots are there, I've shown you in the resonance class, second order control system. What is this? We are doing the analysis of Bode analysis of second order control system, and we have done the actual analysis of second order control system in the resonance class with the resonant frequency omega r and with the resonant peak mr. There is a frequency omega r at which the magnitude is maximum, and that maximum magnitude is given by mr. Okay, okay. Although that analysis was valid for zeta less than 1 by root 2, correct? If you remember, if you keep on revising your notes, so this must be in your mind. For zeta less than 1 by root 2, that analysis was there, and that is why the values of zetas that have been taken, it is less than 1 by root 2 only. It is less than 1 by root 2. 1 by root 2 matlab 0.707. Okay, the resonant peak occurs for point up to 0.707. Beyond that, there is no resonant peak. The resonant peak is just equal to 1, or in decibel, it is 0. Okay. Now, एक point पे आते हैं. Come to the point that the Bode approximation for second order terms is not usually followed. It is not usually followed. For first order, the Bode gives the very good analysis. For second order, Bode is not usually followed. Why? The reason is as the value of zeta increases, see what is the effect. Okay, as the value of zeta increases, this is 0.05. Okay, MR is also inversely related with zeta. Okay, zeta increase hota jayega. Now this is 0.1. Okay, and then this is 0.2, etc. So if the zeta increases, then the actual plot is coming close to the approximate plot. It is coming close to the approximate plot. This one, this level. Okay, that means vice versa. If I say if the zeta decreases, the actual plot is deviating from the approximate plot and error increasing. ठीक है. Like in the case of first order, I told the maximum error. Here also the maximum error is at the corner frequency, but that maximum error in the first order was plus 3 dB. ठीक है, plus 3 dB, and this error depends on zeta. This error depends on zeta. Okay, so maybe for some values of zeta, its error is restricted, but maybe for other values of zeta, the error is maybe not in our range. So that is not usually followed. Apart from that, these are the phase plots. Apart from that, these are the phase plots properly taken from the MATLAB. The phase function, this phase function which I've shown you earlier only, this was the phase function. When plotted in MATLAB for different values of zeta, when plotted in MATLAB for different values of zeta, these are the phase results. These are the phase results. All right. Okay, but still, this is not much useful. This second for Bode plot for second order, but still, what you have to remember now. Let's talk about the point. What you have to remember for your examination, that there can be question, and there has been question in ESE as well as GATE both. There has been questions on this, which somehow directly, indirectly, they are asking you the corner frequency for second order Bode plot. Suppose if I sketch the Bode plot for the second order term, what is the corner frequency? Like for first order, corner frequency is 1 by t. What is the corner frequency for second order? The only thing what is important for you is to remember the corner frequency. That is why I took this analysis, and that corner frequency, guys, is omega n, the natural frequency. The natural frequency. Just that for you it is important. Remember the corner frequency is omega n. Just okay. Time for screenshots. Let me move forward. Take up the screenshots here. No, not really symmetric. Not really symmetric. It is about the peak point. Corner frequency also resembles close to the peak point. No, it's not really symmetric, Deepa. Next one. Next one. Next. Next. Next one. This graph clearly shows that the approximate plot is nearly tangential to the actual plot at high frequency or at the low frequency. That is why these two lines are again known as the low frequency, and this is the high frequency asymptote. And the point connecting the two asymptotes is the corner frequency omega n. Next screenshot, the phase results. All right. Okay, so it's 4:15. Let's conclude this class, and next class means today itself, 5 p.m. Today itself, 5 p.m. Just very shortly, we have the Bode plots class number 3. Okay, what we are going to discuss immediately is the approximate phase results, the asymptotic phase plot. Okay. Yes, yes, Dishan, correct. Just change by positive plus 20. Okay. So next class we are going to begin with the asymptotic phase plot. That is also important to understand, important to learn. Okay. No, usually we don't go for the exponential functions with root locus. Just the reason I explained with the Routh-Hurwitz. The polynomials पे ज़्यादा preferable होता है Routh-Hurwitz and root locus. Okay. We can go by the Taylor's approximation, but that is just an approximation. Okay. What is the actual stability analysis of exponential function like the yesterday's class? Phase margin. Okay. So after solving the asymptotic phase plot, we will have questions. We will have MCQ questions. Okay, so we'll have several variety of the MCQ questions coming up in the next class. Chaliye, bye bye. Take care. See you shortly in 40-45 minutes class starting the next class Bode plus 3. Okay. No, maybe exactly what that question is asking. Just Soumya, quickly tell me the number. Question number. Or Swami, I'm just stopping the stream. The time will go away. Better you can share it me in the doubt box. If you don't remember it right now, share it in the doubt box. That will be better. Chaliye, bye bye guys. See you soon.